Variation. In this video lecture, we're going to talk about direct, indirect, and joint variation. Specifically, our objective, create equations or models using direct, indirect, and joint variation. All right, let's define a few things to make sure we're all on the same page. Variation is how one quantity changes or varies in relation to another quantity. Okay, so that's the general variation. Let's break that down into the three components: direct, indirect, and joint. Direct variation means as one quantity increases, the other quantity also increases at the same rate. Okay? When you see word problems or problems that deal with direct variation, what they're going to say is varies directly or is directly proportional to. Okay, you maybe have seen that in previous classes. And here is the formula when you're talking about direct variation. Y is equal to a constant of proportionality times x. Okay, again, K is called the constant of proportionality. So as x increases, it gets multiplied by something, and the y will also increase. As x increases, the y increases, and the constant of proportionality talks about the constant rate at which it does so. Okay, indirect variation tells us that as one quantity increases or decreases, the other quantity does the opposite. So as one quantity increases, the other quantity decreases at the same rate, or as one quantity decreases, the other quantity increases at the same rate. Okay? Problems with indirect variation will say things like varies indirectly, or varies inversely, or is inversely proportional to. Those are the phrases that will tell you that we're talking about indirect variation. Okay, the equation for indirect variation is y is equal to the constant of proportionality divided by x. So you can see here, as x gets larger, as the denominator gets larger, anything divided by that denominator gets smaller. Okay, so as the denominator increases, a number divided by an increasing denominator gets smaller. Okay? All right, lastly, joint, also called combined variation, is simply a combination of more than one direct and or indirect variation. So we're going to find ourselves with one of these example problems kind of putting these two together a little bit. Some things might be, you may have direct and indirect in the same problem, but you'll still have a constant of proportionality. Okay, let's take a look at what goes on here. Variation problems usually require you to first find K. So you're given enough information to find the constant of proportionality. And then you can use that K and you can write the general formula, and then you can solve problems that involve the general formula. So you find K so that you can write and then use the general formula. Let's take a look at 4 examples to kind of make this a little clearer. We'll do one without one, it's a non-word problem, and then we'll do some word problems because this is often where you see it show up. Okay, y varies directly with x. When x equals 10, y equals 2. What is y when x equals 25? Okay, so here you're told it varies directly. You're given some information to find k, and then you're going to get the general equation and use that general equation in a second situation. Okay, so y varies directly with x. Y is equal to kx. Varies directly. When x equals 10, y equals 2. Okay, 2 equals k times 10. Substitute. T-U-T-E. Hope I spelled that correctly. Okay, we can now solve for k, divide both sides by 10, and k is equal to 1/5. Okay, so we wrote out when y varies directly with x, we started here. We were given the information, an x and a y. We can solve for k using substitution. We find k, and this leads us to the general equation, which is y equals 1/5 of x. And this is the general equation. That's what we're after. Okay, now let's use the general equation to solve for y when x equals 25. Okay, so here's the general equation. Well, I'm asked to find y when x is 25, so I'll substitute 25 in for x, and I come up with y equals 5 when x, and I'll just write down when x equals 25 because that was the question. Okay, so again, y varies directly with x. This is the initial equation to set up. We know some information that'll help us to find the constant of proportionality. That gives us the general equation. Okay, and we can use the general equation to solve any number of problems because we know the constant of proportionality. Now notice here, when x is 10, y was 2. Here, x is 25, x increased, and y increased. X increased from 10 to 25, resulting in an increase of y from 2 to 5. It increased at the same rate. That's why that varies directly. Okay, question number 2. Let's get into some word problems. Keep my sheet straight, I think. Okay, the distance d that an object falls is directly proportional to the square of the time t of the fall. Should have a period there. If an object falls 16 feet in 1 second, how far will it fall in 3 seconds? That's the first question. How long will it take it to fall 64 feet? Okay, let's first set up our equation with the k. The distance an object falls, distance, I'll use d, but they use d as well, directly proportional to the square of the time. So k times t squared. Directly proportional to the square of the time. Distance is directly proportional to the square of the time. Okay, so here we got our initial equation. We know this is the case. If an object falls 16 feet in 1 second, we can use that information. Let's put 16 in for distance. There's the k, and our 1 is the time. It's going to be squared. Now let's solve for k. You can probably see pretty quickly here that it turns out our constant of proportionality is 16. Okay, that gives us our general equation. Distance equals 16t squared. This is our general equation. Okay, now we're going to use it to answer the next 2 questions. How far will it fall in 3 seconds? Okay, so the first one, distance equals 16 times t squared. 3 seconds is the time, so the distance is 16 times 3 squared, 16 times t squared here. And if I do the math, 3 squared is 9, 16 times 9, I believe is 144. So 144 feet is how much it falls in 3 seconds. Okay, let's use it again. How long will it take it to fall 64 feet? Okay, our general equation, 16 equals t squared. This time we're falling 64 feet and we want to solve for the time. So put 64 in for d and let's solve for t. Okay, divide both sides by 16, and I think this comes out to be 4 is equal to t squared. Okay, now we know we square root both sides, but we don't have to worry about the negative in this case. We know that the square root of t squared is t, the square root of 4 is positive or negative 2. but there's no such thing as -2 seconds in terms of falling. So t is just equals 2 seconds to fall 64 feet. Again, we don't have to worry about the negative here in this actual word problem. Okay, let's do 2 more examples. Let's do one with inverse. Okay, make sure my paper's good. I think I'm all right. Okay, example 3. The volume of a gas, V, held at a constant temperature in a closed container varies inversely with its pressure, P. If the volume of a gas is 600 cubic centimeters, when the pressure is 150 mercury, find the volume when the pressure is 200 millimeters mercury. Okay, volume of our gas varies inversely. Volume equals K over P. That's your inverse variation. Again, as P increases, the number divided by it will result in a smaller number. Okay, now let's solve for P. We need to find our constant of proportionality. We're told if a volume of a gas is 600 cubic centimeters, the pressure is 150 millimeters of mercury. Okay, volume is 600, and that's equal to K, the pressure of 150. Okay, now for some it might make sense. This is a fraction. Let's make this a fraction. For those that are unsure about this, and now we have 2 fractions that are equivalent, so we know they form a proportion, and we can cross multiply, and we come up with K is equal to 600 times 150, and I've already done that math. The answer is 90,000. Okay, so we have our general equation. Volume is equal to 90,000 divided by the pressure. And again, this is our general equation that we can now use to solve problems. Find the volume when the pressure is 200 millimeters of mercury. Okay, here's the general equation. Okay, so we know K. We're told the pressure is 200, so we can substitute 200 in for P and find the volume. So it's 90,000 divided by 200. And I've already done the math on this one. 90,000 divided by 200, and yes, I had to use a calculator, is 450 cubic centimeters. Okay, so you can see inversely here. Notice the pressure went up from 150 to 200. The volume went down from 600 to 450. So that's an inverse relationship. As the volume increased, the pressure decreased. Okay, an inverse relationship. Last example, example 4. Let's do a kind of a joint one that has a little bit of everything in it. Okay, the electrical resistance of a wire varies directly with the length of the wire and inversely with the square of the diameter of the wire. Okay, let's forget the rest of this, let's write that down. Resistance, I'll call it R. R varies directly with the length, so the length I'll use is L, so K times L, inversely with the square of the diameter, so over D squared. Okay, so my constant of proportionality, it varies directly with length, that's my numerator. Inversely means I'm dividing it by D squared. Okay, so there's the equation I need to work with to find the constant of proportionality. If a wire 432 feet long and 4 millimeters in diameter has a resistance of 1.24 ohms, find the length of a wire of the same material whose resistance is 1.44 ohms and whose diameter is 3 millimeters. Well, let's first find K. We can find that. We know that this wire that has this length, this diameter, and this resistance. Okay? So these three things go together. Let's find it. So the wire has a length of 432, a diameter. So the resistance is 1.24 is equal to K times the length. The length is 432 feet divided by the diameter squared. The diameter is 4 squared. Okay, again, I'm going to write this as a fraction. 1.24 over 1 is equal to, I'm going to reverse these. I'll put this as 432 over K. I like the letter to come second. It makes it look a little better. 4 squared, of course, is 16. Simplifying this and writing this as a fraction, I see that I have two fractions that are equivalent to one another, so they form a proportion. So I can do cross products. 432 times K is equal to 1.24 times 16. I've already done that math, and that is 19.84. Divide both sides by 432. And I have K is equal to, I'm going to go out to 4 decimal places. I tend to find that that covers me for most things. 0.459. Okay, so again, what's my general equation? I found the constant of proportionality. So I'm going to write this, put in the constant of proportionality. R is equal to K, 0.0459 times the length. You'll notice my L is in cursive, otherwise I get it confused with ones. So I often write, when I use L as a variable, I often write it in lowercase cursive, divided by D squared. Again, this is my general equation, and now I can use that general equation to solve problems. Find the length of a wire of the same material whose resistance is 1.44 ohms and whose diameter is 3 millimeters. Okay? General equation, R is equal to 0.0459 times the length divided by the diameter squared. Okay, what am I told? Find the length, so L is my unknown. The resistance is 1.44, so I'll put that there. I'm looking for the length. The numerator is still the constant of proportionality times L divided by the diameter here is 3 squared. Okay, again, I will rewrite this as, I'll write the left side as a fraction, and I'll clean up the right side by squaring the 3. 3 squared, of course, is 9. And I have two fractions that are equivalent. They form a proportion, so I can use my cross products. Left side, 0.0459 times L. Right side, 1.44 times 9. I've done that math. That product is 12.96. I'll divide both sides by 0.0459 to get L by itself. And the length of the wire comes out to be, this divided by this is 282.35 feet. Okay, so there you have it on variation, direct, indirect, and joint. Keep it simple. Start off with the formula that includes the K. Okay, solve for K to get the general formula, and then you can use the general formula to do whatever you'd like.